All right, we're in the last section, but it's not the last video because I think I'll break up the video into more than one. Um, since it's such a long, there's a lot of slides left. I'll do the remainder of the lecture and then I'll do some examples at the end. The examples are part of the lecture. They appear in your book, but we'll go through them. So we're talking about components of a vector. Now, if you try to add vectors graphically, you can only get so accurate. You'll discover that in the first lab that we do because you have to do the graphical method and the component method. The component method is a lot more accurate. So when let's see. Um, so we're going to use we're going to learn how to use components to add vectors. Uh, you can think of a vector. If you look at the figure, you have vector A, and you have basically you have the three vectors A, AX, and AY. That it forms a right triangle, so that AX and AY are the adjacent and opposite sides, and A is the hypotenuse. So these three vectors form a triangle. If you slide AY to the y-axis, you can see that that's the resolution of A into its vectors. You have the AX component along the x-axis and the AY component along the y-axis. So the cosine of theta is equal to AX over A, the adjacent over the hypotenuse, so that AX equals A cosine theta. And sine theta is AY over A. It's the opposite over the hypotenuse. So AY equals A sine theta. And if you're given the components, then you can find the magnitude of A by the square root of A squared, AX squared plus AY squared. Take the square root of that, and you get A. And you find theta by the tangent inverse of AY over AX, the tangent inverse of the opposite over adjacent. Hopefully this nomenclature is familiar to you. Now what the angle theta actually is depends on the quadrant, and whether the quadrant also determines the sine and the cosine and the tangent when they're positive. There's been, when I was in high school, we had a mnemonic called SATC, and that, I mean, I'll teach you the same one, but it was a little, we used to call it San Antonio Transit Company back before we had VIA. That's a long time ago. I went to high school in the transition from the 60s to the 70s. So we used to use SATC, but reading left to right. Most of the mnemonics use ASTC. And you can remember it. All students take calculus, all science teachers crazy. Just remember the ASTC. And what that means is it tells you which, given the sine, the cosine, and the tangent, which are positive. And in the first quadrant, all are positive. So the sine, the cosine, and the tangent are all positive. If you go to the second quadrant, only the sine is positive. The cosine is negative and the tangent is negative. If you go to the lower left, the third quadrant, you have where the T is, only the tangent is positive. Why? Because you have a negative cosine and a negative sine. Well, the tangent is sine over the cosine, so it's a negative over a negative, so the tangent is positive. And in the fourth quadrant, the last quadrant, as we go counterclockwise, the C stands for cosine. Only the cosine is positive. The sine is negative and the tangent is negative. So AS TC, all students take calculus or all science teachers crazy? Take your pick. I remember the San Antonio Transit Company, but it was left to right that way. So that's, it's just something to help you remember. Let's take a little quiz. Choose the correct response to make the sentence true. A component of a vector is always, never, or sometimes larger than the magnitude of the vector. Is a component always larger than the magnitude of the vector? Is a component never larger than the magnitude of the vector? Or is the component sometimes larger than the magnitude of the vector? And if you think about it, it's never larger than the magnitude of the vector. If you happen to have a 0-degree angle, in other words, a vector that's laying along either, let's say, a 0 or a 90, then the component is the length of the magnitude of the vector, but it's never exceeds it. It's never larger. So that's how we get never. Now, okay, let's go to unit vectors. So unit vectors are a way of expressing equations with vectors. Vector quantities are often expressed in terms of unit vectors. A unit vector is a dimensionless vector having a magnitude exactly 1 along the axes, as you see here. I with it's a little caret hat, a little caret, I caret, j caret, and k caret, and those correspond to x, y, z respectively. So I always refers to the x-axis, j always refers to the y, and k always refers to the z. A lot of the problems you'll only have I and j, so we're only working in an xy plane. But when you're in 3 dimensions, you have the I, j, k unit vectors. The unit vectors I, j, and k form a set of mutually perpendicular vectors in a right-handed coordinate system. So let's go to the next slide. Consider the vector line in the xy plane. The product of the component ax and unit vector I is ax I, and the product of ay and j is ayj. So the vector A can be expressed as AXI plus AYJ. That's the unit vector notation for this vector. This next one, you can have unit vectors in polar coordinates. I've never used it. I won't test you much on this. It's a kind of a confusing concept. We'll just stick with the IJK nomenclature. So we'll skip this slide. Vector addition. Adding vectors using components is a little bit easier when you use components. If you add vectors A and B, all you do is you add the x components together and the y components together separately. So you have r equals, well, let's read the first line. R equals A plus B. So A is AXI plus AYJ, and B is BXI plus BYJ. And so if we separate out the I components, you have AX plus BXI plus AY plus BYJ. So the R is equal to RXI and RYJ, and so you get RX is equal to AX plus BX, and RY equals AY plus BY. Okay, let's look at the next slide. Okay, component method of adding the vectors. You add all x components together and find the x component of the resultant vector. You use the same process for the y components. And then you check addition by the components with the geometric figure. So you can see you have AX and AY, and you have BX and BY. And when you add them up, you can see you have AX plus BX is the length of RX, and you have AY plus BY is the length of RY. Let's see, the magnitude of the vector. The magnitude of R and the angle it makes with the x-axis are obtained from components using these relationships. R is equal to the basically the Pythagorean theorem, Rx squared plus Ry squared. Well, what is Rx? Rx is AX plus BX, and Ry is AY plus BY. So you end up with R equals the square root of AX plus BX squared plus AY plus BY squared. And the tangent theta is the y component over the x component. But what is Ry? Ry again is AY plus BY, and Rx is AX plus BX. So tangent theta is equal to AY plus BY and divided by AX plus BX. And more often than not, you're going to have to use that the theta is equal to the tangent inverse of that fraction, AY plus BY divided by AX plus BX. Now let's extend it to 3 dimensions. You have A and B, you have X, Y, Z components. The A is equal to AXI plus AYJ plus AZK. And you have B is equal to BXI plus BYJ plus BZK. And R is equal to, notice you combine the X components, the Y components, and the Z components. So R is equal to AX plus BXI plus AY plus BYJ plus AZ plus BZK. So you just keep the components together. And if you look at any individual, like R sub Z is equal to AZ plus BZ, and R is equal to the square root of the 3 components, Rx squared plus Ry squared plus Rz squared. And the cosine of theta x is Rx divided by R. Cosine of theta y is Ry divided by R, and cosine of theta z is equal to Rz divided by R. Okay, for which of the following vectors is the magnitude, let me be able to read it here. For which of the following vectors is the magnitude of the vector equal to one of the components of the vector? Is it A equals 2i plus 5j, B equals minus 3j, and C equals 5k? Well, you might think it's either B or C, but only one of these is correct. And it's only C. It bolded it, you can barely tell it. But the fact is, when you're asking about a magnitude, magnitudes are always positive. As a matter of fact, I don't know if they use it here, but quite often, if you want the magnitude of the vector, you put absolute value signs, the 2 vertical lines, you put absolute value signs around like absolute value of A vector, or absolute value of B vector, that it says get the magnitude, and it's always positive. So there, the minus 3 would not be equal to the magnitude. It's a negative component. Okay, and with that, I'm going to stop it. We'll just so the video doesn't go on too long, we'll do the examples in a separate video.